gases. As an example of a chemical reaction that involves a gas, we can consider the inflation of an airbag in a car, which is done by the reaction of sodium azide with iron 3 oxide, and it is initiated by a spark. This reaction produces elemental nitrogen gas, as shown here by the chemical reaction. And so the question then becomes, how many grams of sodium azide are required to inflate a 29.0 liter airbag at 22 degrees Celsius and 739 millimeters of mercury? To answer this question, we need to first of all figure out how many moles of gas, the N2 gas, are going to be in the airbag after it has been inflated. So we're going to use the ideal gas law, and we're going to solve for the N in this equation. So we know that the gas constant is a value of 0.082058 liters atmospheres per Kelvin mole, and the pressure, which is given to us as 739 millimeters of mercury, will need to be converted into atmospheres. And so we know that there are 760 millimeters of mercury for every 1 atmosphere. So divided by the 760 gives us a little less than 1 atmosphere of pressure. In the volume, the units are liters, which are the same as the units in the gas constant, so we don't need to do any conversion there. And it will be the gas N2. And then finally, we need to convert our temperature into Kelvin by adding 273.15 Kelvin to get the required unit for the calculation. We then can plug all these numbers into the ideal gas law. At this point, we have all of the values in the correct units, and so now we can rearrange the ideal gas law and isolate the N. So our equation becomes N equals PV divided by RT. Plugging in all of the values along with their units, we see that the units of atmospheres are going to cancel. We also note that the liters will cancel, and the kelvins will cancel, and then finally we are left with units of moles, and we plug all the values into our calculator, and we come up with 1.164 moles, which having 3 significant digits. At this stage, then, we can recognize that this is the moles of N2, but the question is asking about how many grams of sodium azide are required to do this reaction. So we now need to do some stoichiometry based upon the balanced reaction. So we're going to start with the moles of the N2, and using the mole relationship from the reaction, we know that for every 9 moles of N2, it required 6 moles of the sodium azide, NaN3, and then that will cancel the moles of N2, and finally we use our molar mass of the NaN3, which is approximately 65 grams per mole. And at this stage, the units of moles of NaN3 will cancel, leaving us with units of grams of NaN3, which is going to be the desired answer. So that means we can plug everything in the calculator and come up with the answer with 3 significant digits. And so we have arrived at the answer to the problem. We can derive another equation from the ideal gas law by combining it with the equations for the molar mass and density of a gas. And so it turns out that the molar mass of any compound is equal to the mass divided by the number of moles. as we see here. If we rearrange this equation for n, and then we can substitute that into the ideal gas value of n, we can come up with a new equation that states the pressure times the volume is equal to the mass divided by the molar mass times the gas constant times the temperature. This equation ultimately can be rearranged, and noting that if we bring the molar mass to the left-hand side of the equation and the volume to the right, we now have on the right-hand side mass divided by volume, which is density, and so we can substitute the m divided by v for the symbol for density, which is d, and come up with our new equation, which is P times the molar mass is equal to D times the gas constant times the temperature. Turns out John Dalton made a number of contributions in the study of gases, in addition to his understanding of the atom. And so it turns out that one of his important contributions was that for a mixture of gases, we can talk about the total pressure being the sum of the so-called partial pressures for each of the gases in the mixture. So in the case of the situation for the ideal gas law, we can rearrange it to solve for the pressure, and that gives us P is equal to N, the number of moles, times RT over V. And of course, this would also be true for another gas, which we would identify as gas B, and likewise would be true for gas C. Turns out that we could substitute all of these values into the equation that you see on the top there, and this would then give us a situation where the partial pressure divided by the total pressure has to be equal to the number of moles of an individual gas times the RT divided by V. But then the total number of moles would be in the denominator of the right-hand side, and that would be multiplied by the RT divided by V as well. And of course, the RT divided by V is going to cancel out of this equation, and so we come up with a relationship for the partial pressure divided by the total pressure is equal to the number of moles of the individual gas divided by the total number of moles. So Dalton recognized that in mixtures of gases, as long as they behave like ideal gases, will behave much like a pure gas. And so it turns out that the kinetic molecular theory applies to mixtures as well as it does to pure gases. And so if we have a pure substance with that is in the gas phase and in a container that has a total pressure that is equal to the external pressure, as you see here, that would be exactly the same as an equal number of moles of a mixture of more than one gas, and when the total pressure on the inside and external are also the same. So turns out this is forms the basis for his understanding of the so-called partial pressures, adding up to the total pressure. At this point, we can discuss the concept of a mole fraction. Of course, a fraction is always a part divided by a whole, and in this case, the mole fraction is the number of moles of an individual gas that is present in a mixture divided by the total number of moles of gases in the mixture. So as you see here, the mole fraction is given the symbol of X subscript N, and it's equal to the N of an individual gas species divided by the total number of moles. Turns out then that has to be equal to the partial pressure of that gas divided by the total pressure of all of the gases together. And this then can be related to the sum of the various mole fractions adding up to 1. As an example of how we can use Dalton's law to understand a chemical reaction, if we were to do the reaction between magnesium metal and hydrochloric acid, which would produce an aqueous solution of magnesium chloride and hydrogen gas, it's possible to take and collect the hydrogen gas in the apparatus that you see on the right hand side here, where you have an Erlenmeyer flask and magnesium metal down in the hydrochloric acid. There's a stopper that has been placed into the Erlenmeyer flask with a tube that then allows the gas to be forced over into an inverted graduated cylinder. In the case of the reaction where you have collected 213 milliliters of hydrogen gas over water, the crucial thing is that we are collecting it over water, and the temperature is 21 degrees Celsius and a pressure of 674 millimeters mercury, determine the mass of the hydrogen gas collected. So, in this case, we're going to use the ideal gas law, PV equals nRT, and we're going to try to first figure out the number of moles of the hydrogen gas. To do this, we got to remember we've collected it over water, which evaporates, and therefore the gas that has been collected is a mixture of hydrogen and water. So therefore, the total pressure is the sum of the pressure of the hydrogen and the pressure of the evaporated water. So to just figure out the hydrogen, we're going to take our total pressure and subtract away the pressure of the water. We can then determine what that is by doing looking up the vapor pressure of water at the temperature that we are using, which happens to be 18.7 millimeters of mercury. Subtract that from the 674, and it turns out that then our partial pressure of hydrogen is 655 millimeters of mercury. Now that we know what the pressure of the hydrogen is in the inverted graduated cylinder, we can then use our ideal gas law to figure out our moles. First thing is we need to convert the millimeters of mercury into atmospheres because the gas constants units are in atmospheres. And so we divide by 760 millimeters of mercury for every 1 atmosphere, and that gives us 0.862 atmospheres of pressure. Then we recognize that the volume needs to be in liters, so converting that to liters, we divide by 1,000, and we have 0.213 liters. And the temperature needs to be in Kelvin, so we're going to take 21 degrees Celsius and add 273.15 to it to get 294 Kelvin. At this point, then, we can go ahead and plug our numbers into the ideal gas law, which we rearrange for N, and plugging in all the appropriate numbers and along with the units so that the appropriate units are going to cancel. We're going to end up with moles. All of those values go into your calculator, and you end up with 0.007608, but only 3 significant digits. We then need to go ahead and figure out the mass of hydrogen gas that has been collected. So we need to multiply by the molar mass. And so in this case, the moles of hydrogen times the molar mass of H2, and we end up with 0.0153 grams of hydrogen, which then rounded to our three significant digits gives us our final answer.